Everyone, we're looking at today is combining resistors in series and parallel and combination circuits, just like we did with capacitors. We've got rules just like we did for capacitance. Here the current is going to be the same going through each resistor in a series. There's only one path to go from the positive end to the negative end, so it has to go through each of the resistors. That's what it means to be in series. There's only one path. And since the current's going to be the same, we're going to share the voltage. Each of the bulbs will not be as bright as it used to be because of less energy. Currents will also change. So let's talk about those rules and draw out a circuit with some resistance. Here's our setup. We've got a 12-volt battery with a 4 ohm resistor and a 6 ohm resistor in series. There's only one path to go from the positive to the negative. So let's set this up and show that our rules follow what we said. So we have R1 and R2 here. What we want to do is find the combined total resistance as the charges come out of one end and try to flow through the circuit back to the battery. So if that's the case, whatever amps come out of the battery must walk back into the battery due to conservation of charge. So if I want to find the voltage lost in each of these, I could find the voltage in the first one, the voltage in the second one, and those better sum up to the EMF or the voltage of the battery. Total voltage would equal volts across the first plus volts across the second. And how do we find voltage? Using Ohm's Law, V equals IR. I times R1 times I times R2. That would also equal my total voltage. That would be I times my equivalent resistance. Since the current is the same in a series, it has to go through each of those light bulbs or resistors. That means that I can take out the current in each setup. And what you get in the end is, right here, you get the equivalent resistance is equal to the first resistor plus the second resistor plus however many you put throughout that circuit. Just like capacitors in parallel, resistors in series, you just sum up all the resistors that you have. So it makes it harder and harder for you to get through that circuit. If you look at Ohm's Law here, since the voltage is the voltage of the battery, if you increase resistance, that means I'm going to have to decrease the flow. So the more light bulbs you put in there, or the less the current gets, and the more the voltages are shared among each light bulb. So the more resistors you put in, the dimmer and dimmer the circuit gets. And one other thing with series is if this bulb breaks, or you have a switch and open the circuit, bulb number 1 also turns off. There's only one path, and if you open up the path, there's no way to flow from high to low. So let's try the example then. The example here is the 12-volt battery with a 6 and a 4 ohm resistor. So since those are in series, we can take R1 plus R2, and what that will shrink down to is a battery with one resistor that is equal to 10 ohms. And because I know Ohm's Law, I can tell you that 12 volts over 10 ohms gives me a current of 1.2 amps. So we now know the current that's leaving the battery. That means that 1.2 amps has to walk into this one. And I know that individual resistance, so 1.2 amps times 4 gives me 4.8 volts lost here. And that 1.2 amps continues to walk into the next light bulb. So 1.2 times 6 comes out to 7.2 volts. And then those 1.2 amps walk back to the battery to gain more energy. You get a positive change in voltage as you go across the battery and gain energy. And you lose voltage as you go across each of those resistors. You lose it in the form of heat, light, sound, whatever you need. So that's how we can say that the current stays the same, but the voltage is shared in a series circuit. Let's talk parallel then. In parallel, it's the reverse. The rules are that the voltage is the same for everyone, but now the current is shared, or the current gets split up among all the different branches that you have. So here we have a parallel branch. We've got 3 resistors here. R1, R2, R3, and we've got all those resistors there in parallel. How do I know they're parallel? When the current comes out, it has the option to go across branch 1, has the option to go to branch 2, or it has the option to go up to branch 3. Since it has options, this is a parallel circuit. Because what I could do in a parallel, what I couldn't do in a series, is I could take out one of those resistors in parallel and the other 2 are still attached to the battery. They can still be powered, they can still run just by turning one of those off. So in this case, instead of the voltage being shared, we said the current's going to be shared. So we want to find the total current by looking at the current in each branch. What's the current in the first resistor, what's the current in the second resistor, and what's the current in the third resistor? Well, going back to Ohm's Law, to solve for current, you must do voltage over resistance. That would be the voltage in the first one over R1, plus the voltage in the second one over R2, plus the voltage in the third over R3. Again, the voltages are all the same in each of these since it is in parallel. So there you go, we can knock out all the voltages, and what you're left with is a 1 over R1 plus a 1 over R2 plus a 1 over R3, and so on. So just like we had capacitors in series, we had the inverse equation we had to deal with. Now we have to deal with the inverse equation with resistors in parallel. These equations are on your AP sheet, but it is confusing because it's opposite rules for the different things like resistors and capacitors. So let's try an example with things in parallel. The same two resistors again, but this time we have a 12 volt battery. First thing you might be asked is, what's the voltage in each of the setups? Well, to find the voltage, we know it's parallel and everybody gets the same volts as the battery. So there's 12 volts here and there's 12 volts there. That's nice because now we know the voltage and the individual resistances. I can get you the currents that go through each. There must be 2 amps of current that are going through this circuit, and there are now 3 amps of current that are going to go through this circuit. So remember, power and wattage is based on I squared R, IV, or V squared over R. The main idea, especially with I squared R, the more current you have, the more power you're going to be able to put out. And if you put out more power, you can put out more heat, light, sound, whatever you're looking for. So if we've got 3 amps walking across that first branch and 2 amps walking across that last branch, when they meet here at this junction, that means that those 2 and 3 amps have to combine to 5 amps that are going to go through your circuit. So let's set this up and show an equivalent circuit with those 2 resistors. So there we go, we've got 1 over 4 plus 1 over 6 is our total equivalent resistance. Common denominators here, you could go with 12, so this would be 3 twelfths plus 2 twelfths equals 1 over R. And so remember, that's not your answer is not 5 twelfths. We must combine those and then take the inverse to get our final resistance. So our total equivalent resistance now in parallel is 12 over 5, or about 2.4 ohms. Unlike series, when we have resistors in parallel, when we add resistors together, we get less total resistance in parallel. Well, why would we want that to happen? Well, looking at V equals IR, if I decrease the resistance, that means I'm going to increase the amount of current that has to come out of the power supply. Because I have more and more branches, I need to send more and more amps to each individual circuit. So now I know the equivalent resistance, so my circuit has been simplified to a 12 volt battery and a 2.4 ohm resistor. Let's find the current that comes out. So we have 5 amps that goes into that circuit, but remember, that circuit is technically a 4 and a 6 ohm resistor in parallel. So the 5 amps comes out of the battery, hits the junction, 3 of the amps walk across the first bulb, and 2 of the amps walk across the second bulb. And you can kind of tell based on the resistances who's going to get more current. The easier resistance, more current will flow down the easier path than the hard path. But what happens when we combine series and parallel? Oh my goodness. This is where people start to freak out and people start to panic. It's not that big of a deal. Remember, we love combos and we'd like to see circuits that have more than one resistance or parallel setup. They're puzzles. We need to shrink the puzzle down to 1 resistor and 1 battery, and then open up the puzzle like we've seen before. So here's our setup. We've got a 10 volt battery, has a 2 ohm resistor, a 3 ohm resistor, and 2 4 ohm resistors. So we've got lots of things going on here. What we want to do is highlight where we see series and parallel. And I like to start far away from the battery and work my way back in. Right here, I can see these two are in line with each other. If you go through that first resistor, you must go through the second, so those two must be in series. If they're in series, I can combine these two to an 8 ohm resistor. So there's step 1. Now, let's look at the next set. I see that this resistor and this resistor, there are 2 paths. And when there are two paths, that means that they are in parallel with each other. So if that's the case, I can do 1 over R equals 1 over 3 plus 1 over 8. And to find my equivalence, looks like a common denominator of 24. So 8 over 24 plus 3 over 24 gives me 11 over 24. Total resistance, make sure you take the inverse. You get 24 over 11, which is around 2.2 ohm. We've shrunk down one more time, and now this is our circuit. Again, 10 volt battery, 2 ohm resistor with a 2.2 ohm equivalent resistance. So let's set these up. These two are in series with each other. Why are they in series? Because they're in line with each other. You have to go through both. To do that, I can shrink this down one more time to about a 4.2 ohm resistor. I know the overall resistance, I know the voltage, so I can tell you that the current coming out of this battery is V over R, about 2.4 amps coming out of the battery. 2.4 amps are going to go into this setup, and those 2.4 amps are going to split up depending on how the circuit goes. Let's build the circuit back up and show where each of the values are. Remember, we're looking for currents, voltages, and we can even ask for the power delivered to each. So we know that we're losing 4.76 volts across that first resistor. I know the current going through there. I know its resistance, so I could actually tell you the power that's delivered there. The power lost in that first resistor is about 11.3 watts. When we did capacitors, we were looking for the energy stored in a capacitor. Now, since current's constantly moving, we're looking for the power or the energy delivered to that resistor each second. How much voltage must the second equivalent resistance get? Well, the second resistor, remember, is not a real 2.2 resistor. It's a hidden 3 and 4 and 4 resistor. So we have to break that up, but we know right off the bat that we have 5.24 volts lost in that second bulb. Let's take that 5.42 volts and stretch it out into the other circuits we have. So really, this was the next step. We had a 3 ohm resistor with a hidden 8 ohm resistor. That 8 ohm is not really what it is, but since these two are in parallel, I know that this one has 5.24 volts, and I know this one has 5.24 volts. From that, I know voltage, I know resistance, I should be able to find currents. So if I want to find current, I'm going to take my voltage divided by 3 of the 2.4 amps that are coming out of the battery. 1.75 amps are going across that first 3 ohm resistor, and the rest of that current must be going to the second set of resistors, which is only about 0.655. Adding 0.655 plus 1.75 gives you around 2.4 amps that's going to go back into the battery. So we have our current conserved. Now let's see what happens in terms of that last 8 branch. Oh, one thing we forgot here is we can get the power now in that 3 ohm resistor. I know the voltage, current, and resistance. Whichever one you want to do, I'll do I squared R. I get about 9.2 watts of power in the 3 ohm resistor. Let's go with that hidden 8 ohm resistor. It's not really an 8 ohm resistor, it's really a 4 and a 4 ohm resistor. But I now know how much current is going to flow through each of those. It's going to be that 0.655 amps. And since I know the amps now, and I know each of their individual resistances, I can tell you exactly how many volts I'm going to lose in each. I'm going to lose 2.62 volts in each of these resistors. Adding 2.62 together should give you 5.24, which again, remember, was the voltage of this bulb all by himself. And now I know the currents, the voltages, and the resistances. If I want the power delivered to those two 4 ohm resistors, I'm going to get about 1.71 watts of power delivered in each of those last light bulbs. So if you're going to try and rank these from brightest to dimmest, the brightest bulb would be this first one, the second brightest bulb would be the 3, and then the 4 and the 4 will be equally bright because of the same resistance, same current, and same voltage. So there you can rank the brightnesses from highest to lowest. So that's what we're doing in combo circuits. We are trying to hook up resistors in series and parallel, shrink them down into an equivalent resistance so I can figure out the current that comes out of the battery. Once you've got the current, you can then bring back your circuit into its entirety and stretch out all of the rules that we've had from before. Series, share volts, same current. Parallel, same volts, and you share the current. So So good luck, and we'll talk next time.